Bismillahirrahmanirrahim. In this tutorial, we'll talk about real gases. We're moving forward with a new topic, and we'll solve the selected problems from sheet 1 on this topic. So, to extend our ideal gas model, when we first theorized or talked about the ideal gas law, we assumed two major assumptions. The first one is that the volume of molecules is negligible with respect to the entire container volume at those conditions or ideal conditions. And the second assumption was that there is no interaction between molecules. And this was close to being true in the case of this scenario on the left. So very, very small volume of the molecules compared to the entire container, and since their chance of interacting with each other or colliding with each other is very minimal, so we ignored any interaction forces, whether it's attraction or repulsion between those molecules. And this actually happens when we have a system with conditions of high temperature and low pressure, but in real cases where we have very high pressures or low temperatures, the particles start to get closer to each other, like we see in here, and we cannot ignore the total volume of the molecules with respect to the container anymore, because it takes up some value percent of that container, appreciable value, and since they're close to each other, then we cannot ignore the interaction forces between those molecules anymore, because they will interact with each other. Okay, so to introduce a new parameter, V small, this V small is the molar volume. It's just V over N, the total volume over the number of moles from the ideal gas law that we discussed before. So if we restructure the ideal gas law and express it as a function of this V small instead of the volume and number of moles, we can have this expression, P times V over RT equals Z, which should be 1 if it's an ideal gas, but if it's a real gas and not an ideal gas, it will not be 1. It could be higher or lower. And this actually indicates the volume of the real gas with respect to the volume of the ideal gas. So at the same conditions, temperature and pressure, if Z is more than 1, then the volume of the real gas is higher than the ideal volume of the gas at the same conditions. And if Z is less than 1, then the volume of the real gas at the same conditions will be lower than the ideal gas volume. Okay, and Z is called a compressibility factor, just refer to how compressed is the gas with respect to the ideal gas. So the first and the only model actually that we'll study in real gases is the van der Waals equation, and it's very similar to the ideal gas law. As you can see here, this is a pressure term and this is a volume term, okay, just like the ideal gas, but we're taking into account the interaction forces between molecules and the total volume of the smaller molecules in the system. Okay, so the volume for for the gas molecules now is not the entire volume of the container. It's not all space. There is some volume that's already occupied and cannot be occupied by the same or other molecules anymore. And for the pressure term, we have the interactions signified or indicated by the parameter A, and the 1 over V in here just indicates the chances of interactions between different molecules. So as the volume gets higher, the molecules have less chance of interacting with each other, so the total interaction forces between those molecules will become less or decrease, and that makes sense. Okay. All right, let's see how a real gas would behave in different pressure regions compared to the ideal gas. So when we have very low pressure and a very high volume. In this case, the molecules volume, or the volume of the molecules, is actually much less than the actual volume at the conditions we're talking about. And since the volume is very large, this constant A over V squared, this is a large value, and it's also squared, so it's a very large value right now. This will be very, very close to 0. So it can be neglected with respect to the pressure in here. Okay, so we can neglect this term, we can neglect this term, and we're left with an ideal gas, or an approximation of the ideal gas. All right. At intermediate pressures, the volume will also be intermediate. The total volume of the molecules with respect to the entire, or the total volume, will still be very low. But since the volume is intermediate right now, and the pressure is intermediate, this term is not that small anymore, and we can take it into consideration. So the final form of the real gas, or the compressibility factor, in this case, can take this form with only considering the interaction forces between the molecules. And finally, at very high pressures, we have a very small volume, so we cannot neglect the volume of the molecules with respect to the total volume anymore, so we'll need to take this B factor into account. And logically, we could say that since the V is getting smaller, then this term as a whole is getting larger. Why would we neglect that at higher pressures? But this is true. This term is actually getting larger, but not that large in comparison to the total pressure here in the hundreds or so. So maybe this could be 0.5 or something, and this could be 400. So we can also still neglect that, okay? But we cannot neglect the volume of the molecules, since now the gas is very compressed and they're very close to each other, right? There is interaction forces, and it's higher than these two ranges, but in comparison, or with respect to the total pressure, which is very high, it can be neglected. All right, let's plot those results on this graph between the pressure and the compressibility factor. These are the ranges with the final forms we reached. Intermediate pressure, we will take the interaction forces into account and neglect the volume of the molecules. Very high pressures, we will neglect the interaction forces, and we'll take into account the volume of the molecules. And at very low pressure, we're almost ideal gas. And this is the ideal gas, so we can write here ideal gas will always be Z equals 1. The compressibility factor is 1, indicated by this dashed line. Okay, so in very low pressure region, we'll find that the behavior of real gas is almost asymptotic to the ideal gas. It's very close. We can get close results to the actual values using the ideal gas law, which is very convenient because we can calculate it much easier than using any of the real gas models. In intermediate pressures, we'll find that the real gas actually has less volume than the ideal gas, since the Z is lower than 1. And in higher pressures, the volume will start getting higher, and it will start getting higher and higher as we go and increase the pressure. All right, that's it for the explanation for the real gases. Let's solve a couple of problems to exercise. First problem says, if you know that the hydrogen density at 27 degrees Celsius and 300 atmosphere is 20 grams per liter, calculate the compressibility factor of this gas at these conditions. Okay, so we know that Z is equal to PV over RT, and this is the molar volume. Okay, we have the temperature and pressure given in the question, but we need to get this molar volume to be able to calculate the compressibility factor. So the molar volume is actually the total volume over the number of moles. Total volume can be expressed as total mass over density, and number of moles can be expressed also as total mass over the molecular weight. Masses will cancel out, and we would have molecular weight over density, which is logical because we can express the density as total mass over total volume, or the mass of one molecule over the volume of one molecule. Okay, so we get the molar volume as 0.1 grams per gram mole, and then direct substitution into the compressibility factor relation, we get it as 1.22. And just as a sanity check, this is very high pressure, 300 atmospheric pressure, so we expect that the compressibility factor will be higher than 1, and this checks out. All right. Next problem. If you know that the ammonia density at 117 Celsius and 44 atmosphere is 28 grams per liter, and the density at different conditions is 85 grams per liter. The different conditions are T2 and P2, and this is density 2. This is T1, P1, and density 1. Okay, just like last problem, we get molar volume 1, molar volume 2, and then to get the van der Waals constants for this gas, we can just substitute in the van der Waals equation at conditions 1 and conditions 2. We have two equations and two unknowns. We can just separate out this B into the left-hand side and equate the two equations, solve for A using the calculator solver, and we're left, or we can calculate A and B using this method. So this is actually an experiment that we can do to figure out the constants for different gases if we're tabulating the different parameters for the different gases. We can get a gas in the lab and change the temperature and pressure, measure the density. Once we get two different conditions for the same gas, conditions 1, conditions 2, we can do this simple calculation to figure out the parameters or van der Waals parameters for this gas. Next question. Calculate the pressure of 1 gram mole of oxygen. This is the number of moles at 0 Celsius. This is temperature that occupies a volume of 1 liter. This is the total volume of that gas. Knowing that the van der Waals constants are, this is A and this is B. Okay. So we can just substitute here, and the only unknown is the pressure, but we don't know the molar volume yet. But we know the total volume and the number of moles, which is 1 over 1. So we can get V equals V over N, which is 1 liter per gram mole, right? Then we can calculate the pressure from this relation and simply calculate that using the calculator. It will be 21.76 atmospheric. All right. Next question. Nitrous oxide gas is used as a local anesthetic, and it's required to calculate the weight of this gas that can be stored in a 2-liter cylinder at 30 degrees Celsius and 25 atmosphere. So we have the total volume of the container. The cylinder at the doctor's clinic is V, okay, 2 liters. Temperature is 30 Celsius, pressure is 25 atmosphere. And of course the van der Waals constants, A and B. And we want to calculate the total weight. So we want the mass, total mass here. Okay. So first up, we have the temperature, pressure, A, B. We can calculate the molar volume at those conditions, right? Once we calculate the molar volume and we know the total volume of the container, we can get the number of moles by dividing total volume by the molar volume. We get the total number of moles that could be stored in that container at those conditions is 2.3 gram moles, and the mass would be simply the number of moles multiplied by the molecular weight of that gas. So in total, we can store in 2 liters volume, we can store 100 grams of that nitrous oxide gas at this pressure and temperature, of course. Okay, that's it for the real gases. This is just a brief introduction. There are much more accurate models than Van der Waals model, but it's a very convenient model to start with. It's very close to the ideal gas law and can be manipulated and calculated easily. That's it for today. See you next time.